Today we're going to discuss related rates, how to approach different related rates problems, and how to solve them. First off, related rates problems involve two or more changing quantities, such as dx over dt or dy over dt. Using information given in the problem, you will be asked to find the rate of change of one quantity by relating that quantity to other quantities whose rates of change are known. The rate of change is usually with respect to time. For instance, say you are given a problem in which one person is walking north and one person is walking east. Assuming you are given the necessary details such as the speed they are both traveling or the distance apart they are, using related rates, you could calculate the rate at which the two people are moving away from each other. When solving a related rates problem, there are several steps to follow. 1. Draw a picture of the problem so you can visually interpret the situation, whether it be a cone or a simple 90-degree triangle. If the problem is difficult, you should probably draw it out. 2. Label all the quantities that can change as variables. This could be dx dt, dy dt, theta, or anything of the sorts. 3. Identify the independent variable. In most problems, the independent underlying variable is time. For a problem involving a cone, for example, the independent variable might be h, the height. 4. Next, identify in terms of the variables and their derivatives what is being asked and what is given in the problem. For example, just like we discussed earlier, the problem might ask for the rate of change of a distance between two people walking across each other, or walking away from each other. Number 5. Next, you must form an equation to relate the variables to one another. Next, number 6. When an equation is made relating the variables, differentiate the equation and plug in the independent variables you identified earlier. After this, you can solve for the unknown variable. Without context, the steps for solving a related rates problem looks intimidating, but let's look at a few common types of related rate problems and you'll see how easy it is to solve using the instructions we just discussed. So in this first example, a spherical balloon is being filled up to where its volume is increasing. The area is increasing at a rate of 2 centimeters squared per second. When the radius of the balloon is 3 centimeters, what is the rate of change of the volume? Let's start by writing both the equation for the area and volume of the sphere, just to have it for later. Next, we're going to identify the given variables. In this problem, we are given the rate of change of the area, so we can differentiate the area equation, making it 8 pi r dr dt. Next, identify the variable that is being asked for. In this problem, that variable is the rate of change of the volume. Next step is to differentiate the volume equation, making it 4 pi r squared dr dt. You can next put 2 into the equation because it's given, and set that equal to 8 pi times 3, the radius, dr dt. You can now solve for dr dt, the rate of change of the radius, and plug that value into the differentiated volume equation. Now that you have the rate of change of the radius, you can solve for the rate of change of the volume of the radius is 3 centimeters. It is important to note at this time that when doing a related rates problem, it is very important that you have a calculator with you at all times. The answer ends up being 3 centimeters cubed per second. Our second related rates problem will involve another balloon, but this time we're not concerned with its volume or area, but with the rate of change of its angle with the ground as it rises. Say a balloon rises at a rate of 8 feet per second from a point 60 feet away from an observer. How do you find the rate of change of the angle of elevation when the balloon is 25 feet above the ground? The first thing we're going to do with this problem is draw a little diagram. In this diagram, we're going to label the distance between the balloon's initial point and the observer and the height. Next, we're going to label the given variable, which in this problem is 8 feet per second, the rate of change of the balloon's height.
8 feet per second. And then we're asked to find
Next, identify the variable the problem is asking for, the rate of change of the angle that the balloon is making with the ground when the height is 25 feet.
Y equals 25 feet. So no for sure.
Using simple trigonometry, you can set tangent theta equal to y over 60
Just
feet.
enter y.
Solve for y, which ends up being tangent times 60,
So then we differentiate it.
and then differentiate the equation. This ends up making it dy over dt is equal to 60 times secant squared theta times d theta dt.
So
Next, take the given value, 8, and set that equal to 60 secant squared theta d theta dt.
secant squared theta. So
Give me a theta.
d theta over dt equals.
Finally, solve for d theta dt. When you do so, you get 8 over 60 cosine squared theta, which can simplify to 2/15 cosine squared theta. You have one final step before you can answer this question, and that is solving for
Yeah,
theta.
we need theta.
To do that, you have to take the
Wait, what?
inverse tangent
Inverse tangent
of 25 over 60.
It's a theta. Add that
Oh,
one.
no, now we can just solve for the hypotenuse right here. Are you still videotaping? Twenty-two.
22.62.
When you do so, you get an angle of 22.62 degrees. When you plug that into the equation of d theta over dt, you can finally solve for the answer.
Cosine squared. 22.62.
And then
22.62.
After using the trusty calculator once again, you get an answer of 0.1136 degrees per second.
wait, what?
Let's clean up and do one final example. This last example will involve a cone. Say an inverted cone is 20 centimeters tall, it has an opening radius of 8 centimeters, and is full of water. The water drains out of the bottom of the cone at a constant rate of 15 centimeters squared each second. The water's surface level falls as a result. At what rate is the height decreasing when the water is halfway down the cone? Let's start off by drawing the problem. It is an inverted cone with a height of 20 centimeters. The problem asks what the rate is when the height is 10 centimeters, so might as well label that as well. You can also label the radius, which is 8 centimeters. Next, the problem says that the rate of change of the water is 15 centimeters squared per second, and is asking for the rate of change of the height of the water. Or excuse me, the height of the water of the cone. Next, you can write the equation for the volume of a cone below, because it will be very useful in the near future. That is 1/3 pi r squared times h. Using a simple ratio of the radius, 8 centimeters, to the height, 20 centimeters, you can simplify and set the radius equal to 2/5 h and plug that into the equation for volume. After doing this, volume will be equal to 4/15 pi times h cubed. Now that you have an equation that relates the variables, you need to differentiate it, solve for the rate of change of the volume. final step is to solve for dH over dt, the rate of change of the height of the cone. You can now plug in 10 centimeters for the height, for the height, and for dHdt you can plug in negative 15 centimeters cubed per second. After doing the necessary calculations, you get an answer that happens to be negative 15/16 pi centimeters per second. And that is your answer. In conclusion, related rates problems all follow the same basic steps that we outlined earlier in this video. Follow aforementioned steps and you'll be able to tackle any related rates problem, whether it's a cone or a
I really hope he doesn't get this off.